Ever wonder what makes your socks stick together right out of the dryer? Or, what holds the actual atoms in your body together? Believe it or not, it's the same invisible force, electrostatics. It's one of the universe's fundamental rules, and once you get it, you start seeing it everywhere.
So what is this mysterious force, really? Well, the answer is something you've definitely heard of, but maybe haven't thought too much about: electric charge. It's just a basic property of matter, like mass, and it is the absolute key to unlocking our entire electrical world. All right, to really get a handle on this invisible force, we've got to start at square one. We have to ask the basic question: what even is charge? Okay, so think of it this way. Just like a thing has mass, it also has electric charge. It's just a core part of what makes stuff, well, stuff. And it turns out we can study it in two very different states. And this right here is a really important distinction. See, when charges are moving, think of electricity flowing through a wire. That's what we call electric current. The study of that whole world is called electrodynamics. But what if the charges are just sitting still, just holding their ground? That is the world of electrostatics. And for this explainer, that's exactly where we're going to live, in the world of charges that aren't going anywhere. So if these charges are just hanging out, not moving, how do they interact? How does a charge over here talk to a charge way over there? Turns out there's one incredibly simple and incredibly powerful rule that runs the whole show. This is it, the golden rule of the game. A positive charge and a negative charge, they pull right toward each other. But if you put two positives together or two negatives, they push each other away. It sounds almost too simple, right? But believe me, this one simple idea has absolutely massive consequences. And this is how we put some numbers to that push or pull. It's called Coulomb's law. Now, don't worry about the formula itself. Just get the big idea. It says two main things. First, bigger charges mean a stronger force. That makes sense. But second, and this is crucial, as you pull those charges farther apart, the force gets weaker. And not just a little weaker, it drops off fast. That's a huge deal. But wait a minute, how does a charge here know about a charge way over there? I mean, they're not touching. How can they push or pull each other across totally empty space? The answer is just a beautiful concept called the electric field. I just love this analogy. A single charge isn't just sitting there. It's actively changing the space around it. It creates this invisible field of influence. So when you bring a second charge into that field, it doesn't feel the first charge directly. No, it feels the field that's already there. The field is the middleman that does all the work. So if this field is invisible, how in the world do we picture it? Well, physicists came up with this brilliant tool called electric field lines. For a positive charge, just picture lines shooting straight out of it in all directions, like rays from the sun. For a negative charge, do the opposite. Picture all the lines pointing straight in, like water going down a drain. And here's the best part. Wherever those lines are bunched up really close together, the field is super strong. Where they're spread far apart, the field is weak. It's basically a weather map for an invisible force. Now, drawing lines is great for one or two charges, but what if you have, say, a billion of them? Trying to calculate the force from every single one would be an absolute nightmare. But thankfully, a genius named Gauss gave us a truly elegant shortcut. To get this shortcut, we need a term that sounds kind of fancy: electric flux. But don't worry, the idea is super simple. Imagine you're holding a window frame out in a rainstorm. The flux is just a count of how many raindrops are passing through your window. Same idea here. With electric fields, flux is just a count of how many field lines are passing through a surface. That's it. And this brings us to the magic trick, Gauss's law. It says that if you draw any imaginary bubble in space, the total number of field lines poking out of that bubble depends only on the total charge you've trapped inside it. So you don't need to worry about the details of every single little charge. All that matters is the total charge you've caught in your imaginary bubble. It is a massive, massive simplification. So we've talked a lot about forces, the pushes and pulls between charges. But that's really only half the story. Now let's shift gears and talk about energy, because it turns out that a charge's location inside an electric field is everything. And here's why. The electric force is what we call a conservative force. Now, that might sound technical, but you're already an expert on this because of gravity. Think about it. When you lift a heavy book, you're working against gravity, right? That effort you put in doesn't just vanish, it gets stored in the book as potential energy. If you let go, that energy gets released. It's the exact same principle for charges.
Let's really walk through this. Picture a big positive charge just locked in place. It's creating its electric field all around it. Now you grab another little positive charge and you start trying to push it closer. You can feel it fighting you, right? That repulsive force? Well, the work you're doing, the effort you're putting in, isn't lost. It's getting stored up in the system as electric potential energy. The second you let go, whoosh, that stored energy is released and the charge flies away.
Okay, but what if we want to talk about the energy of a particular spot in the field before we even put a charge there? That's what electric potential is for. It's the amount of potential energy per charge, and we know it by a much more common name, voltage. Yep, that voltage. So when a battery says it's 9 volts, it's telling you how much of an energy kick it can give to every little bit of charge. It's the energy landscape that makes all our gadgets work.
So let's just quickly run through the whole journey we've been on. We started with the idea of charge itself. Then we saw how these stationary charges create invisible electric fields and how they push and pull on each other based on Coulomb's law. We found that amazing shortcut with Gauss's law. And finally, we connected forces to energy and saw that a charge's position in a field gives it potential energy, which we measure as voltage.
And that kind of brings us to our final, pretty mind-bending thought. We've just been talking about tiny little particles, but these exact same rules, these fields, these potentials, they're what bind molecules together. They power stars, they orchestrate the cosmic dance of entire galaxies. So the real question is, how do these simple, elegant principles scale up from the microscopic to shape the entire universe? It's a truly profound question. Thanks for joining us for this explainer.